Imagine a time when no one truly knew what an atom looked like, when matter itself was a mystery hidden behind equations and guesses. Tonight, we travel back to the moment when a simple idea about electrons transformed chaos into order and changed physics forever. This is the story of how the atom revealed its secrets. At the beginning of the 20th century, physics appeared confident, almost complete. The laws of classical mechanics and electromagnetism had explained the motion of planets, the behavior of waves, and the flow of energy with remarkable success. It was natural, therefore, to assume that these same laws would govern the smallest building blocks of matter. Yet when we turned our attention inward, toward the atom, this confidence began to dissolve. The atom did not behave as classical physics demanded, and this failure was not a small error, but a fundamental contradiction. According to classical theory, an atom was imagined much like a tiny solar system. Electrons circled a dense, positively charged nucleus in continuous motion, just as planets orbit the sun. But classical electromagnetism carried a troubling implication. Any charged particle in motion should continuously radiate energy. An orbiting electron, therefore, should steadily lose energy, spiral inward, and collapse into the nucleus within a fraction of a second. If classical physics were correct, atoms would be unstable, matter could not persist, and the world as we know it could not exist. Yet atoms clearly did exist. Matter was stable. Chemistry functioned reliably. The universe had not collapsed into a cloud of radiation. This gap between theory and reality was deeply unsettling. It revealed that classical physics, for all its triumphs, was incapable of describing nature at very small scales. The failure was not due to poor measurement or experimental error, but to the assumptions embedded in the theory itself. Another profound difficulty emerged from the study of light emitted by atoms. When gases were heated or electrified, they did not emit light across a continuous range of colors, as classical theory predicted. Instead, they produced sharp, discrete spectral lines, each at a very specific wavelength. These lines were like fingerprints, unique to each element. Classical physics offered no satisfactory explanation for why atoms should emit energy only at certain precise frequencies and not others. Attempts were made to force classical ideas to fit these observations, but each attempt led to further contradictions. The equations could be adjusted, the models refined, yet the results remained unsatisfactory. The atom seemed to resist every classical interpretation imposed upon it. This resistance was not accidental. It was nature itself, signaling that our way of thinking needed to change. The crisis extended beyond atomic structure into radiation itself. Experiments on blackbody radiation and the photoelectric effect showed that energy exchange did not occur smoothly and continuously, as classical theory required. Instead, energy behaved as if it came in small, indivisible packets. This idea was deeply uncomfortable, for it challenged the very foundation of classical continuity that physics had relied upon for centuries. What made this failure particularly significant was its philosophical implication. Classical physics was built on determinism, continuity, and certainty. If the initial conditions of a system were known, its future could be predicted precisely. The atom, however, refused to conform to this worldview. Its behavior suggested limits, discontinuities, and rules that could not be derived from classical reasoning alone. It became increasingly clear that the atom was not simply a smaller version of familiar mechanical systems. The rules governing everyday objects could not be scaled down indefinitely. At the atomic level, nature followed principles that were new, subtle, and deeply counterintuitive. The failure of classical physics was therefore not a defeat, but an invitation to rethink the relationship between theory and reality. This realization marked a turning point in the history of physics. The inadequacy of classical ideas at the atomic scale forced physicists to abandon long-held assumptions and accept that knowledge of nature is not absolute, but conditional. Each theory has its domain of validity, and beyond that domain, new concepts must emerge. The atom taught us humility, reminding us that understanding nature requires not only mathematical skill, but also the courage to question the foundations of our own thinking. When I introduced the idea of quantized energy levels, it was not meant as a rejection of reason, but as an acceptance of experimental truth. The atom demanded rules that classical motion could not supply. Electrons, I proposed, were not free to exist at any arbitrary distance from the nucleus. Instead, they were confined to specific orbits, each corresponding to a fixed amount of energy. These orbits were not chosen by convenience or geometry, but by strict conditions imposed by nature itself. In these allowed orbits, electrons behaved in a way that seemed almost paradoxical. Though they were accelerating charges, they did not radiate energy. They remained stable, neither collapsing inward nor flying away. This stability was not explained by classical mechanics, but it was essential for the existence of matter. The atom, once seen as fragile and temporary, became a system governed by precise and enduring rules. The key to this stability lay in the concept of quantization. Energy within the atom was not continuous, but divided into discrete levels. An electron could occupy one level or another, but never the space in between. There were no gradual transitions, no smooth paths from one orbit to the next. The electron could only move between levels by making an abrupt change, absorbing or emitting a definite amount of energy in the process. These transitions explained atomic radiation in a way that classical physics never could. When an electron absorbed energy, it jumped to a higher orbit, one farther from the nucleus. When it lost energy, it fell to a lower orbit, releasing energy as electromagnetic radiation. The frequency of that radiation was determined precisely by the difference between the two energy levels. In this way, the atom became a clockwork of energy exchanges, governed by strict numerical relationships. The allowed orbits themselves were defined by a simple but profound condition. The angular momentum of the electron could take only certain values, proportional to a fundamental constant of nature. This restriction had no classical justification, yet it produced results in perfect agreement with observation. The size of the orbits, their energies, and the frequencies of emitted light all emerged naturally from this assumption. What made this idea especially powerful was its ability to bring order to atomic behavior without describing the electron's motion in complete detail. It was no longer necessary to imagine a precise trajectory at every moment. Instead, the focus shifted to what could be known and measured, the energy states and the transitions between them. This marked a subtle but important shift in the philosophy of physics. The quantized orbits also introduced a new way of thinking about causality at the atomic level. The electron did not move smoothly from one energy to another. It changed state abruptly. This challenged the classical notion that all physical processes must be continuous. At the smallest scales, nature appeared to favor discreteness over smoothness and limitation over freedom. Although the model retained familiar elements such as orbits and particles, it carried within it the seeds of a deeper transformation. Quantization suggested that physical quantities, once thought infinitely divisible, were, in fact, constrained by fundamental limits. These limits were not imperfections of measurement, but intrinsic features of nature. In this way, quantized energy levels and electron orbits served as a bridge between the old and the new. They preserved enough classical structure to be intelligible, while introducing ideas that pointed toward a radically different framework. The atom was no longer a miniature solar system governed by Newton alone, but a system shaped by rules that hinted at an underlying quantum order, one in which stability, radiation, and structure emerged from restriction rather than freedom. One of the most striking successes of the model lay in its ability to explain atomic spectra. a problem that had resisted understanding for decades. When scientists observed light emitted by heated gases, they did not see a smooth rainbow of colors. Instead, they saw a pattern of sharp, well-defined lines, each appearing at a precise wavelength. These spectral lines were reproducible and unique to each element. Yet, classical physics could not explain why atoms should emit light in such an orderly and selective manner. Before this explanation, spectral lines were treated almost as empirical curiosities. Mathematical formulas, such as those describing the hydrogen spectrum, could predict the positions of these lines with remarkable accuracy, but they offered no physical insight. The equations worked, but they did not tell us why nature followed them. This gap between calculation and understanding was deeply unsatisfying, for physics seeks not only to predict, but to explain. By introducing quantized energy levels, the mystery of atomic spectra became intelligible. Each spectral line corresponded to a specific transition of an electron between two allowed energy states within the atom. When an electron moved from a higher energy level to a lower one, it released energy in the form of light. The color or frequency of that light was determined entirely by the difference between the two energy levels involved. This relationship brought extraordinary clarity. The discrete nature of spectral lines was no longer mysterious, but inevitable. Because electrons could occupy only certain energy levels, the energy they emitted or absorbed could also take only certain values. Continuous spectra were forbidden, not by experimental limitation, but by the structure of the atom itself. Hydrogen, the simplest atom, provided the clearest demonstration of this principle. Its spectrum, once a puzzle of disconnected lines, emerged naturally from the model. Each series of lines could be traced to electrons transitioning between specific orbits. The numerical agreement between theory and experiment was exact, lending strong support to the idea that quantization was not a mathematical trick, but a fundamental property of atomic systems. More importantly, this explanation revealed a deep connection between matter and radiation. Light was no longer an external disturbance imposed on atoms, but a direct expression of their internal structure. By studying the light emitted by an atom, one could infer the arrangement of its energy levels. Spectroscopy thus became a powerful tool, allowing scientists to probe the invisible architecture of matter. The success of this explanation extended beyond laboratory experiments. By analyzing the spectra of stars, scientists could determine their chemical composition, temperature, and motion. Elements discovered on Earth were identified in distant celestial bodies through the same spectral signatures. The atom, once thought too small to matter on a cosmic scale, became a key to understanding the universe itself. This achievement also reshaped the relationship between theory and observation. Spectral lines were no longer isolated data points to be fitted by formulas after the fact. They became predictions of a physical model rooted in clear assumptions about atomic structure. The theory did not merely describe what was seen, it explained why it had to be seen that way. Yet even in this success, there were signs of limitation. While the model explained the hydrogen spectrum with precision, it struggled with more complex atoms. Additional interactions and effects appeared that the simple picture could not fully capture. Still, the essential insight remained intact. Atomic spectra arise from quantized energy transitions, not from continuous motion or arbitrary radiation. Through this explanation, the atom revealed itself as an orderly system governed by strict rules. Light, once viewed as a wave spreading smoothly through space, now appeared as a messenger, carrying precise information about atomic change. Each spectral line marked an event, a transition, a discrete exchange of energy that reflected the underlying quantum structure of matter. The ideas introduced through the atomic model did not stand alone. They pointed toward a much deeper transformation in the way physics understood nature. By accepting quantization as a fundamental principle, the model challenged the belief that all physical quantities vary continuously. This challenge became the foundation upon which modern quantum theory was built. The atom, once treated as a minor exception to classical laws, became the stage on which entirely new principles were tested and refined. The notion that energy changes occur in discrete steps reshaped the interpretation of physical processes. It suggested that observation at the smallest scales does not reveal smooth motion, but structured transitions. This insight encouraged physicists to question the completeness of classical descriptions and to seek new mathematical frameworks capable of capturing these discontinuities without contradiction. As research progressed, it became clear that the atomic model was only an approximation, yet it served a critical purpose. It preserved enough classical imagery to make the new ideas accessible while introducing concepts that classical physics could not accommodate. In doing so, it prepared the scientific community for more abstract formulations that would soon follow. The development of wave mechanics and matrix mechanics expanded upon these early ideas, replacing definite orbits with probability distributions and operators. Yet the concept of quantized states remained central. Even as the image of electrons circling the nucleus faded, the idea that atoms possess discrete energy levels endured. The model thus acted as a conceptual bridge, guiding physics from visualizable motion toward abstract representation. This transition also altered the role of measurement in physics. In classical theory, measurement was assumed to reveal properties that existed independently of observation. Quantum theory, however, suggested that certain properties could only be defined through interaction with measuring instruments. The atomic model hinted at this shift by emphasizing observable quantities such as spectral frequencies rather than unobservable trajectories. The philosophical consequences were profound. Determinism, once regarded as an unassailable principle, was replaced by statistical prediction. The certainty of cause and effect gave way to probabilities constrained by precise mathematical laws. This change did not weaken physics. It expanded its reach, allowing it to describe phenomena that classical certainty could not encompass. The emergence of quantum theory also transformed the language of physics. Concepts such as complementarity and uncertainty arose from attempts to reconcile particle-like and wave-like behavior. The atomic model contributed to this dialogue by demonstrating that mutually exclusive classical pictures could each capture part of physical reality without providing a complete description on their own. Education and research were equally transformed. Students of physics were now required to think beyond mechanical analogies and accept abstraction as a necessary tool. The atom was no longer a simple object, but a system defined by rules that defied everyday intuition. This intellectual shift fostered a new generation of physicists equipped to explore domains previously thought inaccessible. The influence of quantum theory extended rapidly into chemistry, solid-state physics, and nuclear science. Chemical bonding, electrical conductivity, and atomic stability all found explanation within the quantum framework. None of this progress would have been possible without the initial step of acknowledging quantization in atomic systems. Through this evolution, the atomic model retained its historical significance. It marked the moment when physics accepted that nature at its most fundamental level demands a different logic. The birth of modern quantum theory was not a sudden revolution, but a gradual realization, and the atom was its first and most compelling teacher.